Welcome students. In this video we shall see a problem on ideal and real gases in which we are going to find the partial pressure of the individual constituents and then we will be finding the total pressure. The question is like this. A vessel of 0.35 meter cube capacity. So I am having a vessel, the capacity of which is 0.35 meter cube. This contains carbon monoxide and air. A vessel of 0.35 meter cube capacity contains 0.4 kg of carbon monoxide and 1 kg of air at 20 degrees Celsius. So carbon monoxide is 0.4 kg and the air is 1 kg. So both are at a temperature of 20 degree Celsius. In this problem I had to calculate what is the partial pressure of each constituent. So I am having carbon monoxide and air. So instead of air I can say nitrogen and oxygen. So air is a combination of nitrogen and oxygen. Also it is given the gravimetric analysis of air is 23.3% oxygen and 76.7% nitrogen. So nitrogen will be 76.7% and oxygen will be 23.3%. It means in 100%, 76.7% will be nitrogen and 23.3% will be oxygen. Or I can say out of 100 kg, 100 kg air, 76.7 kg will be nitrogen and 23.3 kg will be oxygen. If for 100 kg nitrogen is 76.7 kg, then for 1 kg air I will be having, you have to divide by 100 on both terms. So we will be having 0.767 kg nitrogen and 0.233 kg oxygen. So the mass of nitrogen is 0.767 kg and that of oxygen is 0.233 kg. So if you add this, I will be getting the mass of air, that is equal to 1 kg. The mass of carbon monoxide is given as 0.4 kg. The volume is given as 0.35 meter cube and the temperature is given as 20 degrees Celsius. To convert to Kelvin you have to add 273. So this will become 293 Kelvin. So this is the given data. Apart from this, the molecular weight is given. The molecular weight of carbon monoxide is 28 and the molecular weight of oxygen is 32 and molecular weight of nitrogen it is 28. Also we know that the universal gas constant, or I can say RU, universal gas constant RU is equal to R into molecular weight. So this is characteristic gas constant and this is universal gas constant, and mu is the molecular weight. So in this problem the characteristic gas constant is not given, so for each of the gases I have to find what is the R value. The product of R and molecular weight is same for all the gases. In this problem I have to find what is the R value for oxygen, nitrogen and carbon monoxide. So R is equal to universal gas constant divided by molecular weight. So if I rearrange this equation and write it for carbon monoxide, I can write like this: universal gas constant divided by molecular weight of carbon monoxide. So that is 8314 divided by molecular weight of carbon monoxide is 28. So 8314 divided by 28, I will be getting 296.9 joule per kg Kelvin. So how I am getting this joule per kg Kelvin? Because the unit of universal gas constant is joule per kg mole per Kelvin divided by unit of molecular weight is kg per kg mole. So kg mole gets cancelled. Remaining I will be having joule per kg Kelvin. That's how I arrived at this R unit. Now the gas constant value for oxygen. So universal gas constant divided by molecular weight of oxygen, that is 8314 divided by 32. So this will be giving 259.8 joule per kg Kelvin. Similarly, I can find the R value for nitrogen. So here nitrogen is becoming R value for nitrogen. So universal gas constant divided by molecular weight of nitrogen, that is equal to 8314 divided by 28. This is 296.9 joule per kg Kelvin. So now I have to find the partial pressure of each constituent. So how many constituents are there? I am having carbon monoxide, nitrogen and oxygen, 3 constituents. So partial pressure of carbon monoxide, partial pressure of nitrogen and partial pressure of oxygen. These 3 I have to find, and the total pressure is the summation of all this. So if I find the partial pressure, I can get the total pressure. So now we have to understand what is partial pressure. So in the problem it is given as a container of some volume. Here I am having carbon monoxide, oxygen as well as nitrogen at some pressure P. But if I consider the same container, and in the container if carbon monoxide alone exists at the same temperature, you consider temperature T and here the same temperature. So temperature and volume are same. But here what is there is only carbon monoxide there. So what will be the pressure it will be exerting? So that pressure is called as the partial pressure of carbon monoxide. Similarly, if oxygen alone is there in the container, then the pressure due to that oxygen in that container is called as partial pressure of oxygen. So we know that PV is equal to mRT. So if a gas is assumed to exist alone in this container, then I can write the partial pressure of that into volume, the volume, total volume. So partial pressure into total volume is equal to mass of that constituent into the gas constant value of that particular constituent into temperature. So the partial pressure equation becomes Pi is equal to Mi into Ri into T divided by V. So this equation I have to apply to get the partial pressure of carbon monoxide. So mass of carbon monoxide into R value of carbon monoxide into temperature divided by volume. So mass of carbon monoxide is 0.40 into R value of carbon monoxide. So that is 296.9. 296.9 into temperature. So the temperature is 20 degrees Celsius. I can write it as 293 Kelvin. And volume is 0.35 meter cube. So volume is given as 0.35 meter cube. So volume is 0.35. So here mass is in kg, R value is in joule per kg Kelvin, and temperature is in Kelvin, and volume is in meter cube. So kg gets cancelled, Kelvin gets cancelled. Remaining I am having joule per meter cube. Now what is joule? Joule is Newton meter, and at the denominator I am having meter cube. So if I cancel this, I will be getting Newton per meter square. So if I substitute this values, I will be getting the partial pressure in Newton per meter square. So if I solve this, I will be getting 419 Newton per meter square. Also we know that 1 bar is equal to 10 power 5 Newton per meter square. So 1 Newton per meter square is equal to 10 power minus 5 bar. So to convert this Newton per meter square into bar, I have to divide by 10 power 5. So this will be giving you the partial pressure of carbon monoxide as 0. So you have to divide by 10 power 5. 1, 2, 3, 4, 5. So 0.994 bar. So this is the partial pressure of carbon monoxide. Now I have to calculate the partial pressure of nitrogen. The same equation, but I have to substitute the mass of nitrogen, R value of nitrogen into temperature divided by volume. So the mass of nitrogen is 0.767. 0.767, and R value for nitrogen is 296.9, and temperature is 293 Kelvin divided by volume 0.35. This will be giving the partial pressure as 190,636 Newton per meter square. So if I want to convert it into bar, I have to divide by 10 power 5. So 1, 2, 3, 4, 5. 5 digits I have to bring before. So 1.906 bar. The partial pressure for oxygen can be found using the equation P is equal to mass of oxygen into R value for oxygen into temperature divided by volume. So mass of oxygen is 0.233 and R value for oxygen is 259.8 and temperature 293 Kelvin divided by volume 0.35. So on solving this, I will be getting the partial pressure of oxygen as 50675.1. So unit will be Newton per meter square. If I have to convert to bar, divide by 10 power 5, I will be getting 0.506 bar. So this is the partial pressure of oxygen. Now the total pressure is asked. The total pressure is equal to the partial pressure of nitrogen plus partial pressure of carbon monoxide plus partial pressure of oxygen. So the partial pressure of oxygen is 0.506 and the partial pressure of carbon monoxide and the partial pressure of carbon monoxide is 0.994 and partial pressure of nitrogen is 1.906. So if I add all this, I will be getting the total pressure P, that is equal to 3.406 bar.